Hello everyone, and welcome to today's workshop, Marine Data for Arctic Ocean for the Copernicus Marine Service. So my name is Gaëlle Hénaff Sterbik, and I'm a training officer at Mercator Ocean International, and I'll be your host for today. So as you know, we will have a 2 days workshop, and today we will have more of an introductory session where we'll tell you about what the Copernicus Marine Service is about and what sort of data you can find and what sort of applications you can do with the data we provide to you. So before we start, we are going to go through some house rules and guidelines to help you follow this workshop in the best possible way. So first, please do not use the chat that you see on your right-hand side for question. You can use it for small talk or say hello to each other, but if you have a more technical question or if you have any other type of question, you can use the Q&A section. So it's on the website on the top bar of your page, and you will find the Q&A button. And if you click, you will see an area dedicated to the Q&A, and that's where you can ask our speakers your question for today. Speaking of your speakers, so we will have many interesting presentations. So first, we will start with an overview of the Copernicus Marine Service. So I will do that. Then we will have Rezak Khouas from Mercator Ocean International. He will do a demonstration of MyOcean Viewer Pro. And after that, we will have 4 use cases from external speakers. So the first one will be Jiping Xie from the Nansen Environmental and Remote Sensing Center. Then we will have Ana Maria Mancho from the Spanish National Research Council. Then Keguang Wang from the Norwegian Meteorological Institute. And finally, we will have Susanna Winkelbauer from the University of Vienna. So it promises to be a very interesting morning, and I hope you will enjoy it. So we will jump right with the introduction to the Copernicus Marine Service. So it's a little overview about what the service is about, and just to introduce you to it if you are not familiar with the service yet. So Copernicus is a program created by the European Union. So it's a European fully funded program dedicated to the observation of the Earth and to better understand different systems of the planet. It includes 6 services, so the atmosphere, marine, land, climate change, emergency management, and security service. And it provides information and free of charge open source data products about all of these different systems. So obviously the Marine Service focuses on monitoring the marine environment. You access the service through the website of Copernicus Marine. So it's free to access the website and to download any product. There you will find an extensive catalog of products. All of them are scientifically qualified and they are user-driven, so they are constantly upgraded and improved. And we also take into account the experiences of users of the service. So what kind of data does the Copernicus Marine Service provide? So it provides data on the blue, the green, and the white ocean. So the blue is all about the physical component of the ocean, so the currents, the temperature, the waves, the wind. The green ocean is the biogeochemical component of the ocean, so everything that has to do with the phytoplankton, the nutrients, the chemical composition. And finally, the white ocean. So it's the ice coverage, the ice velocity, so all that has to do with the ice. Then you can find, these are just a few examples, and in terms of temporal and geographical coverage and the type of data the service provides, it is quite varied. So we have in situ data, we have satellite observations, which are used to validate or model data. And you can find that the data that are measured right now, so we have real-time data, but also from the past all the way back to 30 years. So it's called reanalysis or multi-year data. And we also provide forecast 10 days into the future. And in terms of geographical coverage, So we do cover 5 areas or 6 regions, so the global region all around the world, and smaller areas all around Europe. We also have on the website a visualization tool that you can use. So it's called MyOcean Viewer. We will have a demonstration just after my presentation of that. So you have 3 versions, the Learn, the Lite, and the Pro. And you can select a project to see it or visualize it in a very fun way. So it's very interesting and it gives another perspective to the data. We also provide specific products like ocean monitoring indicator or data related to the climate. So in this case, the monitoring indicators are key variables to help us understand how the ocean is, the health of the ocean. So it's also accessible and free, and they also cover the 30 years back, so long-term analysis. We also try to provide information, and one of the ways that we do that is by publishing a yearly report on the state of the ocean, and we also provide the Ocean State Report Summary, where we try to target more or less scientific communities, so more policymakers and the media or even the general public. And also to make sure that the information can get to everyone, we did that by creating 2 pages called the Ocean Explainers and the Ocean Climate Portal, where we explain some oceanographic concepts or current threat that the ocean is facing. And we try to explain it to everyone, actually. So also the Ocean Climate Portal just gives a perspective on the indicators key variable of the climate and the ocean, but like I said, in a more accessible way for everyone. So as you can see, we try to reach a bit of everyone, but it's the data that we provide and the information, it responds to different needs. So that's what we call the blue markets. So it goes from science to innovation to policies, but also to coastal services and economy sectors. Also, for example, so today you will hear about 4 use cases, so practical applications of the data from the Copernicus Marine Service. But in the website, you will find many more examples, and we invite you to go have a look and to learn from these examples. Also, if you are yourself a user of our data, we invite you to submit your use cases, your project as a use cases. We are always interested to learn more about how the data is being used everywhere in the world. And also, beside the data, we also provide training like this one, and we try to make sure that the data is not only accessible, but we can help people use it. So like I said, we have training like this one, but we have also webinar, hackathons, forum, and all type of events. So to try to engage with the users. So that's all for me for today for the introduction. So I hope you got a little glimpse of what the service is about.
Hello everyone, I hope you're doing well. I'm Rezak from the user support team from Copernicus Marine. Today I will be presenting one of the main tools used to visualize and download Copernicus Marine data, which is the MyOcean Pro Viewer. To access it, really simple. You just have to go to this section here, Ocean Visualization Tools. Click on it, and then you will be getting 3 different options. So we have the MyOcean Learn, which is dedicated to beginners. We have the MyOcean Lite, a more advanced but intermediate version of it. And then we have the MyOcean Pro Viewer. To access the tool, just click on Explore. And now we are on the interface of the tool. So here we have 2 predefined layers, which can help you to get started with the tool. So we have the seawater potential temperature and the mass concentration of chlorophyll in seawater. Various options are available, as you can see. So you can either swing with your mouse to get better access on the interested region. You can also zoom in or zoom out with your mouse wheel to get better visualization of your data. You can also change the projection in case you want to visualize the North Pole projection or the equatorial projection or the South Pole projection. Here on the left, we have a window which basically allows you to add various layers to display your data. So here, as you can see the eyes here, when the eyes is in blue, that means that the data is visible. When it's not, that means that the data is not visible. You can also alter the order of the two layers just by maintaining your mouse and drag it down to make the one below the other, and the visualization will be given to the layer on the top, as you can see here. If I change it again, then I have my old visualization back. So let's add a layer. Since today it's an Arctic presentation, I'm going to visualize the sea ice thickness. So I'm going to add an Arctic product. For that, you have just to click here on the plus to add a layer. And then we will be accessing the data store where all the products of Copernicus Marine are available. So we have nearly 300 products. And as you can see, we have products from models, also from satellite, and also from in situ observations. Like this one here, just going to find the in situ to give it to you. Anyways, there is also in situ observations. You can just see it here in the description of the product itself. And as you may have seen it, each product has its own specificity. So we have the spatial extent, we have the spatial resolution, we have also the temporal extent as well as the spatial resolution, and various variables that are contained in the product itself. And here on the left, we have various filters that can help you to find your the product of your interest. So let's give an example for today. I want to visualize an Arctic variable. So I know that I want to choose within the Arctic area. So for that, we're just going to select Arctic oceans. And then we'll be getting 52 different products in this category. And now I know that I want to get a sea ice variable, for example. So just here in the main variable section, just select the sea ice variable, and then you will be getting 17 different variable to select. So here you can also choose to put your time range if you know the time range that you need. Also the depth range, in case it's a 3D model, then you will be having latitude and longitude as well as the depth level. So let's say I want to add this product, just click on it and you will be getting some information about the product itself. So it's basically a small presentation of the product with various information on the variables and also the type of the product. If you go here to the notifications section, you will be getting also information about the breaking changes that occurs on the product itself. So we have the incidents, the improvements, as well as the maintenances. If you want to visualize a given notification, you just have to click on it and you will be able to see the details. Here in the data access section, if you click on it, you will be getting a list of the data sets that are contained in the product itself. And for each data set, you have 3 different options. You can choose to click on form, then you will be getting the access to download it. You can also click on browse to retrieve the original data in their original form as the way they were produced by the producers. WMTS allows you to access the WMTS service. And as you can see here on the top, we have 3 different options also, subsets, files, and maps. So let's say if you click here on the information icon, then you will be redirected to the related article to this one. Of course, the subset is a function related to the Copernicus Marine Toolbox, which I'm going to be presenting tomorrow. For those who want to attend, I will be presenting the main features of this tool, also which allows to download Copernicus Marine products. So going back to our tool, here we have also the possibility to contact the user support or the help center in case you have a question. And here you have a documentation section which lists the user manual, the quality information documents which contain technical and scientific information about the product itself. We have the synthesis quality overview, license, and how to cite. Here also you have the option to share the product if you need, and just click on it and it will automatically generate a link of the product. Now let's add the variable to our tool. Just click on add to map, and then you'll be getting different variables related to the sea ice. Of course, you can add another variable in case you are interested in another variable. Just click here, scroll down to all layers, and you will be getting all the datasets that are contained in this product, and then you can choose another variable. So for this one, we will choose the sea ice thickness. So just click on add to map, and as you can see, it's being added. Now to get better access to the variable, I'm just going to hide the two first layers and change the projection since it's in the north. Go into the North Pole projection, and here is my data. Now, if you see here on this Windows, we have 5 different icons. So we have the download icon, which I'm going to present later on. We have the information icon, which basically allows you to plot the windows that I've shown you earlier about the product's specificity. We have also the layer icon, which allows you to add another variable in case you want to change the variable to display. Just choose another data set and another variable, and you will be good. Here we have also the gear icon, which allows you to customize your plot. So let's say here you want to change the opacity, you can just choose to adjust it like this way. Here also you have the color map option, which allows you to revert the display of the data if you want to revert it. You have also here the steps icon if you want to customize your visualization. Click on it and you will be changing the visualization. And here you can choose to automatically, or you can manually put the minimum and maximum values, or you can choose to do it automatically. Just click on automate, and that will like this. I'm going to zoom in to get better visualization. So let's click on automate. That will automatically define the approximately minimum and maximum value based on the visualization that you have chosen. So here at the bottom, we can also add steps or remove steps and configure it manually also. Great. And now we have also the possibility to hide the out of range values. If you can see here in my in this scale, which corresponds to my minimum and maximum values, if I click on here, if I want to mask these values, I just can click on it and I will be hiding all the values that are out of this range. And now there is also another option if I want to display my data in vectors or in just solids. For that, I will change the variable because this option is not available for the sea ice thickness. So for that, I'm just going back to my equatorial projection and change the variable. Let's say I want to take another variable. Let's see. So as I said, go into the layer icon here, select a data set. Let's say the seawater velocity. A better example to show you this. And so let's hide this one. Okay, the seawater velocity, and if we go back to the gear icon for this variable, then we have another option here, the style option. So here I have the possibility to display the data in solids or solid plus vector. As you can see, I will be getting solid plus vector visualization or only vectors. So that's basically it. And now I can choose also to remove this variable since we don't longer need it. Just click here on the cross and the variable will be removed. Going back to our main variable, North Pole, okay. So here I also have the option to disable or enable the log scale. Just click on it and you will be, that would be good. Here at the bottom, I have the time scale, which allows me to display the data based on the time range of the product itself. If I go beyond 2024, you can see that the data is not available. Same thing. If I go earlier than 2022, then the data is also not displayed simply because it's not within the time range of the product. I can also choose to zoom in with your mouse wheel to get the data based on the day and even the hour, or zoom out, or you can just click on reset zoom to get the initial form of the time scale. Here on the right, I have also a depth range, depth level scale. In case you want to adjust the depth levels, you can just choose with your mouse and select manually the depth that suits you. Here also we have 5 different options. So you can put points on your visualization. You can also put lines. And to disable the option, just click on the escape button on your keyboard and you will be good like this. To get better visualization, you can choose to hide this window by clicking here, hide control block. And now you can also put areas. So click on it, go back and select your area. Again, escape on the keyboard to disable the option and we're good. And now, as you can see, we have 3 different selections. So in each selection, I have also various informations here. So here we have the coordinates of the area as well as the surface of the area I've selected. In this one, I have the coordinates of the point. And in this one, I have the coordinates and the length of the line I have selected. In each one, as you can see, I have graphs that basically tells you the evolution of the variable, the sea ice thickness variable over the time. And if you click here on the 3 points, you will be getting also various options. You can expand the graphs, adjust the axis. You can choose to export it to NetCDF, CSV, or SVG format, or you can also remove the graph itself or remove all the graphs. So let's keep in mind that if you want to do the export process, you have to be logged in. So let's say I'm logged out. Then you will no longer be having these options, as you can see. So I'm gonna log in again. And we're good. Other thing, you can choose to merge a selection within the other. Let's say I want to merge this one in this one. You just maintain it with your mouse and drag it on the top of the other selection, and you will be merging it. If you want, in case you want to take your visualization, your data exploration further, you can choose to do this process. Really practical. And now let's remove the selection here. Okay. So another option, which is a recent option, is the import icon here. If you click on it, you can choose to import presets, which is basically selecting a predefined geographical area in case you want to download your data. That will be helpful for you. You can choose also to go in this one, recents. Here, it allows you to import the presets that you have selected. You can also import a WKT file, a GeoJSON, or a shape file. in the settings icon, you can, as you can see, you can log in or log out. You can change your maps based on the theme that suits you. You can also change the geometries as well as the minimum graph elevation, show additional statistic, and many other options related to your visualization. And now, going back to our window here, I will present the download icon. If you click on it, again, you will be getting 3 different options to download your data. To do it, you can browse files. If you click on it, you will be getting the original files. So let's say you want to download the 2023 files, the data files, you can just click on 2023 and you will be getting, let's say you want to download data. Let me retry it because because we're supposed to get the data based on the year and also the month. Okay, 2022. Normally, we were supposed to get 2022, and for 2022, all the months going from January to December, and then you will be getting your data files in here. So let's say you want to download your data of September 2022, just click here on it, and you will be getting the data. Move on to the other option, the automate option. Here, let's say in case you want to download your data automatically, you just go back to your screen here and you can choose to define an area. Of course, you can put manually your geographical information and download it, or you can use a simple way by clicking on define on map and define here your area of interest. And then, as you can see, the information are automatically filled. Same thing for the date range. If you can put it manually or you can do it as a map. So let's say here I want to download data from the 6th of February 2023. Just click on it, go back as a map. And yes, here it was supposed to select the 6th of February. Same thing here to the 8th, for example. It's supposed to take here to select the 8th of February, and you can choose to, with it, also download another variable along the way. Then you can select the also download option. So to automate your downloading, you can just click on automate and you will be getting 2 different templates. So you have the command line interface templates and the Python API. So here it's related to the subset function, of course, which is a function of the Copernicus Marine Toolbox that I'm going to present tomorrow. And based on the interface that you need, the support that you are working on, you can just copy it, paste it, and download your data. And the last option is to download the data simply by clicking on download, or you will be downloading it. Of course, here, just a small info, you cannot download more than 300 megabyte of data. So you are limited in terms of memory. So let's say here, if you want to download data from 2022 to 2024, let's say. Normally here, if you select a larger amount of memory, it will tell you that the data cannot be downloaded. In this case, it's not, it's less than 800, so you can download it. Here at the top, we have 3 different options. So I will begin with the eye information icon. If you click on it, you will be getting a small definition of the MyOcean Pro viewer tool. also some keyboard and mouse tips that you could use to easily manipulate the tool. So let's say, for example, I want to hide this window. I just have to click on the escape button on my keyboard and it will be hidden. Here in the share icon, you can choose to share your activity just by using a link, an image, a video, or an embed link. Just keep in mind that this allows you to share exactly what you are doing in the tool. So let's say you have explored this area and you want to share your visualization, then you could do it with these 4 different ways. And last, you have here the message icon in case you want to access our user support platform. So here you can go and type on help. If you type MyOcean Viewer Pro, then you will be getting a bunch of articles that can help you to get started with the tool. Also here, you can choose to message Blue, which is our chatbot, and ask him a question. So let's say how to use the MyOcean tool. So what Blue is going to do is going to search in all the available information in our user support office, and it will came with the best answer to your question, followed at the end by a bunch of links to help you to get started with the MyOcean Pro viewer. So here, for example, if you click on the main feature of MyOcean Pro viewer, you will be getting the main features that basically I've presented earlier, which will help you to get started with the tool and manipulate it easily. You can also find the various questions that are being asked about the tool and consult those questions, and you can find the response for them. In case the answer of Blue didn't satisfy you, you can choose to talk to a person just by clicking on this option. One of our team, the user support, will be glad to help you out with that. So with that being said, I think all the main features have been covered. I hope you enjoyed this presentation. If you have questions, please ask them. I will be glad to answer them. And I thank you all.
Thanks a lot, Rezak, for your nice presentation. So we have a few questions for you. And so we will move on to the Q&A. So the first one about if the data is fully available or if we have to pay for it. So no, all of the access and the download of the data is free. So you can check out on the website of Copernicus Marine Service. You have a data access tab, and you have all of the products, and you can download everything you want for free. Okay, this question. How do you define the resolution of data you download? For example, if I want a day average instead of hourly. So I think we have products that are daily average, if I'm not mistaken.
Each product has its own specificity, like I said in the presentation. So you have products where you can find daily, hourly, monthly, or yearly data. So you just have to look in the description of the product itself. And yes, you will be getting those data, and based on also on the data set that you choose to download. So there is an article that speaks about the nomenclature of the data, which can help you to understand how each syntax of the data set refers to the temporal resolution of the data sets. So that can help you to distinguish between the hourly, daily, and monthly data.
Okay, thanks a lot. So then we have this question. It's almost the same as the following one. Why any limit actually both on direct download and possibly on APIs? So why, and also why is the 350 megabyte limit on data download?
Yes, it's the way that to download the data manually, like I said, you have a limit size. If you try to download it manually, you have a limit size. This is why the Copernicus Marine Toolbox, which I'm going to present tomorrow, as I said, is have the advantage on this point that in case you want to download a large amount of data, we recommend using the toolbox, because in that way, as long as your device can support the amount, then you can download as much data as you want.
Okay, thanks a lot. So, and just to know, why is there this 350 megabyte limit? Is it a mandatory data? Do you know?
No, the limit size is 800 megabytes. It's just that the example that I have presented in the seconds ago didn't fill this option. I was trying to show you that we have this limit, but even if the range that I've selected still doesn't reach the 800.
Okay, thanks.
So this is why I didn't get the message that the dataset is too large to be downloaded.
Okay, great. Thanks. Can we use automatic data using R? I'm not sure I understand the question.
Yes, we can use automatic data using R. Yes. If you want further information about how to use R to download your data, there is an article related for that. You can just type downloading Copernicus Marine data using R, and you will be getting an article in the Help Center which speaks about the subject.
Okay. Are there any scientific reasons for the color scales available in the interface? I think it depends on the parameters you used.
Yes, the color scales are available to customize your visualization in case you want to change it. Because if you are visualizing various layers and displaying various variables, that could be really useful for you to use various options to display it and customize your visualization. That allow you to manipulate the tool easily and to get the best way to to visualize first, and also to download the data you need. So it's a good way, it's an interesting way to explore the data.
Okay, thanks. So we have time for 2 more questions. So this one, is there a complete online training session with details that help beginners to start using this data with machine learning? So for the training, I don't think we did a session with machine learning, but maybe you already have some article on the website. I don't know if you know.
For this one, I can. I think not in machine learning.
Yeah.
I don't think. Yes.
Yeah, but it's a nice idea. So maybe we will do a training
Yes.
with the data for machine learning. So I will keep this one on the side to think about it for another training session. How can we retrieve data constantly as datasets updates using Python? I think use the Copernicus toolbox, no?
Yes, you can use the toolbox, and there is various ways to do it. You can either set up a script because each dataset is updated I think 2 times a day, and you can consult this. Also, you can consult this in the Help Center. There is an article which speaks about the subject. You can see when the data is being updated, and you can set up a script with using the toolbox. You can use the subset function, for example, set up your info, your data that you need to download, and yes, it will automatically be downloaded, and you will be downloading the updated data. So yes, it's possible.
Okay, great. And so that will be the last one before we will have to move on. Are there ways to repurpose the existing data as obstacle datasets, potentially to identify barriers, challenge, or inefficiencies within the system? Very technical question.
Ways to Okay, in this, yes, indeed, it's a very technical question. For that, you can In case, yes, if you have a question for this example, for this question, you can contact us to via the chat, like I said, and we'll be taking this question and submit it to the related department, and yes, we will be getting back to you with the best possible answer to it, because for right now I can't really give you the answer to it.
Okay.
So yeah.
Yeah, I will put the question on the side, and we will provide a better answer in the post-event report. Okay. So thank you, Rezak, for the question and the presentation. We will see you tomorrow for the Copernicus toolbox.
Thank you again. See you tomorrow.
See you tomorrow. Bye.
Thanks. Bye. Thank you.
So it's time for Jiping. So whenever you want, the floor is yours, and welcome to the training.
Thank you, Clara, and it is a good time for me, and thank you organizing. I have a chance to share our experience on our work about sharing the sea ice surface salinity deviation in the Arctic Ocean. My background is ocean modeling and data simulation. So much focus on how to develop the nice Arctic reanalysis. So today I looks, yes. Why mentioned salinity here? Because salinity is important in our Arctic region. For example, if you know this figure, you can see this is show some such stratification control index in the global ocean. The red color means is the most important is temperature. The blue color means is the salinity becomes more important to control the stratification. So it's why in Arctic region we should know more details about salinity, how to impact the ocean density. Here I give two examples. Woodgate, Palalat, some paper talking about the warming and the freshening of Pacific inflow shows the Pacific winter water, the equivalent depths from 100 to the 50 meters in the past 30 years. It makes reconstruct how the Arctic Ocean mixed. Another case is from the Lockett paper 2022. By their work, they verifies and propose sea ice formation in the polar region is possible because the salinity gradients and halocline keeps the water column stable despite the intense cooling. So how is salinity when in conservation in the modeling? For the model, in the ocean always contains a lot of water than salt, usually about only about 3.5% in the total. So salinity always take the roles to present how the different water mass exchange and mixed. For example, in our Arctic region, on like the diagram, you show the inflow water from Pacific through the Bering Strait and output the from Straits, and also on the south of boundary we have some Atlantic water going inside Arctic region. So Pacific inflow almost a little bit along the one switch up is increased in the recent years. Also for the sea ice, also some seasonal melting, they can bring a lot of not purest water, but we can equally about 6 PSU water inside the ocean. Other fresh water is coming from the rivers, also precipitation. So it is balanced between the pure water, fresh water, and sea ice melting water, and exchanges water mass in the ocean. So always we use fresh water define some reference salinity. For example, for the Arctic, for the Atlantic water, we more often use the 34.8 PSU. But in the recent paper from the Sarah Lodge, they recommended in the terms of such budget will be used to obtain the unique result for quantify and compare the salinity. Because it always, when you define the reference salinity, always confuse the fresh water. But based on this recommendation, we should know how accurate for the salinity. So here I borrow two figures from my colleagues from Bertino. Thanks for the Rezak give the detailed so many useful introduction about MyOcean. These two plots also is obtained from the MyOcean, and the left panel shows the sample mean in September in 2021, and this is a sample mean from the 4 data simulation tip models. They are from the Mercator, CMCC, ECMWF, and the UK Met Office. And from the left panel, I can show some sea ice as the white colors. Outside, you can see some salinity, the pattern. And the right panel is I would like to highlight here. It is an ensemble standard deviation. You can see the red color means it's a salinity is largely uncertainty about more than 2 PSU, and they emerges in both C and Car C and laptop C. Yeah, even they assimilate data, but still is quite uncertainty in the Arctic region. There are out of many uncertainty factors in impacts for that. So let's say here I also want to mention we have used some institute data from the Copernicus Marine Service. It is easy to find that data, and here I give example to based on this data set, we can plot in all the profiles located in the Arctic region during the 28 years from 1991 to 2018. You can see during the many years, still some region we don't have some data covered from this data set. For example, in the Eastern Cyprian Sea, there are very few salinity profiles. So it's one big limited for the salinity. We still some space is not clearly. And here I present one work is a surface salinity intercomparison in our paper in 2019. We compared the different satellite data and climatology and observatory analysis and reanalysis, 2 products from the Copernicus Marine Service. The left panel shows satellite results in September to the one month average. So of course there's some different still some difference you can because visualization. And here I just highlight the scattered plots. For example, compare the Topaz 4 and BEC satellite data. The 2 lines, the blue and the light blue and the pink line shows the gap. It means this gap shows us the possible benefit if we assimilate the satellite data into our models. So continually, we can, based on this expected benefits, we can do some data experiments. And this table shows we'll simulate different data source, for example, sea level anomaly, SST, and the profile, concentration, CS drift, CS thickness. All the data downloaded from the Copernicus Marine Service. And also we use the Copernicus marine toolbox can be downloaded, can be used. And another surface salinity from satellites, we use the ESA project about Arctic salinity and provide this kind of data. It's a 25-kilometer resolution. And the control run is experiment 0, and other 2 experiments with additional to assimilate surface salinity to compare the impact. Here we use the top parts. It is coupled data simulation, ocean and sea ice. Based on the ensemble computer. In this system, we use the 100 members to do that. And I show the result will be about use based on the ensemble mean. And in this case, we also use the independent profile to validate our result. They are, of course, they collected all the data during the experiment time periods. We try to collect all the independent valuable data. And this panel shows follow the clues in you can see the 3 lines. The green color is show the control run. The red line will simulate surface salinity data version 3. And the middle it shows a previous version 2. You can see the red line mean square error could be very small compared to other 2 runs. Clearly, it shows some benefits from the assimilation this kind of data. And in a separate different, for example, in Booth Sea and the Greenland Sea, we plot in all the surface salinity based on using the scatter plot. And in the left is a control run, middle is assimilate version 2. The right panel column shows this assimilate version 3 result. On average, we can see the benefits we have root mean square error can be reduced 10 to 20%. And even for the monthly surface salinity in 8 months, in August and September, and focus on the right panels, we can show the difference compared to the control run. And when we simulate version 2, near the coast region, the surface salinity becomes fresher. When we simulate version 3, becomes more fresher. There is some big difference compared to these 2 versions. And also when we assimilate this data, we can find some benefits about SST. Here I showed some SST increments during the half year's experiments. On average, it looks very small, but in some region, we can still find some difference. For example, along the Kara-Sea, when we assimilate version 3, the SST increment becomes more small. And also we can diagnose in the freshwater increment the changes in the 2 cases. This can be modified by assimilation, this kind of data. So here, give a summaries when we assimilate this data. Yes, for the surface salinity in the global data, still has a larger uncertainty in the Arctic region. And we try to assimilate surface salinity. We can get some better results. This data can be assimilated in our Realysis products. This can be downloaded from Copernicus Marine Data Store. Also from this Copernicus Marine Service, maybe you can just here, I just give example. If the keywords surface salinity, you can find many other good surface salinity data. For example, this one is this combined data from SMOS and SMAP. SMAP is NASA satellites. It's measured data set. We keep interesting to use this kind of data to improve our results. Thank you.
Thank you very much, Jiping, for the presentation. It was really interesting. so we have a few questions for you. So we will go to the Q&A session. So, okay, so I have internet issues, so I can highlight question, but the first one is a general question about what is an ensemble mean?
Yeah, thank you. This is a ensemble mean, as I mentioned, when we do data simulation, we need to define a background error covariance between the model and observation. In our case, we use based on a 100 model ensemble to provide this kind of background covariance link the model and observation. But this is the ensemble mean. This is just we use all the members to do the average to do the, then get the best estimates about for the model states, then provide it as our into reanalysis product.
Okay.
If I explained clearly.
Yeah, I think it was clear enough. I understand it, so it should be fine. Thanks a lot. So the next question about how do you filter out your outliers in the regression?
I guess this question is linked to I gave the scatter plot when we do the regression between all the observations scatter plot. Actually, if yes, it should have many different approach. For example, in general, we can define the standard deviation is not so big if some observation points is outline. For example, it's out the three times standard deviation, you can take off. It's very general the way, but in this case, we don't find this so strictly limited for our case, this study.
Okay, thanks a lot. We also put the DOI of your publication on the InWeek chat for people to have a look if they want. Thanks a lot for the explanation. Okay, is the Cora in situ accessible, and are all of the data sets like temperature, salinity, chlorophyll, TSS available here? Sorry.
Yes, yes. First question, the Cora in situ data is available on the Copernicus Marine Service. They also provide the great product, as I know. And the second question, yes, temperature, salinity, chlorophyll, I'm not sure because I much focus on the physical part. For the biology model, maybe my colleague can be answered. I didn't look at no. But I guess it depends what kind of profile we can collect it in this data set.
Okay, I see. Thanks a lot for the precision. Okay. Next question. What is the instrumentation used for observing salinity? Can it be observed by satellites?
For the instrument observation is quite limited. With most salinity observation can be available from the profile. And the profile, of course, we can depend on different observation platform. For example, most profile, you just follow the cruise and mooring, that's all. But satellites, I don't think they can observe because the satellites always observed near surface, and it's limited for the satellites.
Yep.
I don't think they can provide so many details on the surface. Maybe AI could be.
Yeah, I think the most efficient is still boats and buoy and stuff like that for now, for the profile, like you said. Okay. What are the spectral signature of salinity? So kind of almost the same question. Where can we get the spectral signature library?
Yeah, yes, I think this question is not easy to answer for me. Yeah, because depends how to define here the spatial signature. If we just on the locally, for example, if you have some you have a longer time series, could be easy to get the 1 point. But for on the space, almost it's very difficult, almost impossible to get the very special, because so far we don't have some big enough Bayesian scales observation about the salinity. Almost just, of course, we have some salinity. Only surface under surface is so many uncertainty.
Yeah, yes. Okay. Still on spectral signature, does Cora in situ data have spectral signature?
Yeah, I think for example, if some more in data is possible, but I didn't do this way. Yeah. Sorry for that.
So is it recommended to use the reanalysis data over the classic analysis data in the MyOcean data?
I think the question is very interesting.
Yeah.
As I showed in some figures, if you remember, I show the four products we did it, the average and ensemble mean. This is still uncertainty. I think each product is quite important because it shows one example for one possibility. For that case, no data is perfect. Depends what kind of your topic. But I think it's a good way. All different products can provide this kind of ensemble to help you to make them. The further judgment how to use this kind of data to improve your understanding of your scientific question.
Yeah, it's true. And okay, also the same question still about reanalysis. Is there going to be a reanalysis for the data of the years after 2020? So yes.
Yes, I think yes. And every year we continually extend our reanalysis. For example, in the Arctic Ocean sea ice analysis, every year we update it two times, and we will be continue. Yeah.
So yeah, we have the reanalysis data of all of the years. It's regularly updated. So that was the last question. I don't think more will come. So thank you, Jiping, for your nice presentation and the Q&A session. It was nice having you with us. So yes, we put the link of your paper on the chat, and also it's also available on the website for people to download. So thanks again for that and for your participation. We will have a small break, so a 10-minute break. So feel free to chat with each other on the chat or go grab a coffee or a tea, and we will come back in 10 minutes. So see you later, everyone. And thanks again, Jiping. Welcome back, everyone. I hope you had the time to grab a coffee or take a little break. So we will move on to the presentation of Ana Maria from the Spanish National Research Council. So welcome, Ana, and thanks for joining us. So whenever you want, the floor is yours to start your presentation.
Presentation.
Oh,
Okay.
I can hear you now.
Now I see. Okay. So thank you very much to the organizers for giving me the opportunity to give this presentation in this very interesting workshop. And also thank you very much to all the attendants for your interest in this presentation. This presentation is going to be split in two parts. In the first part, I will provide some concepts and ideas that are necessary to understand the second part, which is more focused on the concept of Lagrangian transport in the Arctic waters. So how does a mathematician, let's see if it is working. I think, okay, how does a mathematician sees the surface of the ocean? A mathematician sees the surface of the ocean as a vector picture, where in each point of the ocean there is a vector that is pointing out in the direction of the current. So to understand Lagrangian transport, oceanographers count with Lagrangian observations, Lagrangian datasets, as the one I am showing in this picture, where I am showing the paths followed by 48 quasi-Lagrangian floats that were released in the North Atlantic in 1972 and were tracked for almost 2 years. And then typically oceanographers do the representation of these floating drifters in this schematic representation that is called spaghetti diagram. And you can see it is quite erratic. And the idea of this presentation is, in the first part, to provide tools to try to find order patterns from this disorder. So, as I have mentioned to you, a mathematician sees the ocean surface as a vector field, as this one, where there is arrows that point out in the direction of the currents. And to understand the transport question, the most important thing is to know where fluid parcels go, as in this, as we see here, where fluid parcels go. And we know that from the purely advective approach, fluid parcels follow trajectories that are solution of this differential equation, where here V represents the velocity field. And in this presentation, this velocity field is going to be provided by datasets from the Copernicus system. So to try to find order on these fluid parcels, we are going to use ideas from dynamical systems that are due to Poincaré, a mathematician who, in the context of celestial mechanics, introduced concepts that are exportable to the context of the ocean. And Poincaré ideas, what try to do is, instead of representing fluid parcels individually on the ocean surface, what he proposes is to look in the ocean surface for a partition where fluid parcels behave similarly. So in this way, within a partition, all fluid parcels behave similarly, and fluid parcels that belong to different partitions behave in a very different way. So this is the idea, to find this kind of partition in the ocean surface that distribute particles with similar behaviors and separate particles with different behaviors. So to build this geometrical construction, a very important concept is the concept of hyperbolic trajectory, and fluid parcels in the neighborhood of those hyperbolic trajectories behave in a way that they elongate along, they elongate along the unstable direction, and these blobs contract along the unstable direction. So in the neighborhood of an hyperbolic trajectory, a blob, if we wait long enough, get aligns along a curve that I am depicting here. This is the curve. And then this curve is called attracting material curve because all fluid parcels tend to get aligned along it. And also it is called unstable manifold. Is the mathematical concept related to the idea that this is linked to the unstable direction of the hyperbolic trajectory. And then these curves behave as barriers to transport because fluid parcels tend to get aligned with it and they do not traverse this barrier. So in time-dependent flows, these barriers may be very, very complex, as I am depicting here. And the question is if this complex curve really exists in nature. And the answer is that yes, they exist and they are rather universal. As you can see, for instance, in these satellite images from the NASA satellite. So what we see here is the coast of Greenland, where the ice is melting and is going towards the sea, and all the little pieces of ice are getting aligned with these very strange curves that are exactly the attracting material curves I have explained before. So this is the idea, no? Then another important concept is that I have explained how fluid blobs evolve forwards in time in the neighborhood of this hyperbolic trajectory. But now I am asking myself where these fluid parcels are coming from. And fluid parcels in the neighborhood of an hyperbolic trajectory are coming from another curve that is called a stable manifold because this curve is related to the contracted direction of the hyperbolic trajectory. And as time evolves, these curves tend to shrink and be collected with within the neighborhood of the hyperbolic trajectory. I am calling these curves repelling material curves. So it is possible to find also trajectories in the neighborhood, not only in the interior of the ocean, but also in hyperbolic trajectory attached to the coastlines. And I am depicting here an hyperbolic trajectory attached to a coastline in a configuration of detachment trajectory. And then in this case, the stable manifold is aligned to the coast and the unstable is transversal to it. And blobs in this neighborhood evolve being collected in the neighborhood of the hyperbolic trajectory, and then the material is ejected towards the interior of the ocean. So this configuration is very important because we are going to discover this in the Arctic with important implications for that. So these curves are referred to the material and attracting curves. As I have said, may be very complex in the interior of the time-dependent flows and are referred to Lagrangian coherent structures. And it is difficult to compute them. In this presentation, I am going to compute them with the tool of Lagrangian descriptors. And these curves with this tool are highlighted with this very sharp change in color. You can see delicate lines, very complex lines at the background. And those lines are these curves that are attracting and repelling material curves. So just a note on where this tool is coming from. I am providing here a set of reference where the tool of Lagrangian descriptors was introduced. And these Lagrangian descriptors are computed as arc length of trajectories that are integrated forwards and backwards in time. And then we are going to apply these ideas on Copernicus datasets, particularly in data from the Arctic, because this data is reliable and also they are available in open access. And we think that the use of dynamical system tools on these accurate velocity datasets open new possibilities to address important ocean challenges. And this is what we are going to do next. So we are going to compute these Lagrangian coherent structures on the Arctic. All what I am going to explain here is a summary of some conclusions that appear in this article here that, that was published in 2018, jointly with Jiping, the previous speaker, and also many other co-authors. So the Arctic Ocean has a wealth of petroleum and gas resources, and I am presenting in this map all these resources distributed in the whole Arctic coast. All these resources that I am marking here are not under exploitation, but it is known that particularly in North America, the exploitation of these resources is increasing. And one important question is if we are setting risk too high regarding this exploitation. And this is what I am going to try to answer with the tools I have been presenting. So to this end, we have computed in the Arctic Ocean, we have computed these Lagrangian coherent structures. And I have marked here the presence of an hyperbolic trajectory in a configuration of detachment. I said that it is detachment because it's rather close to the coast of North America, that is here. And all these areas are areas where all these resources I have mentioned are being exploited in North America. And what we see is that very close to this coast, you find the presence of this stable manifold aligned with the coast that whatever leakage that is produced near the coast would be transported towards this hyperbolic trajectory in the interior of the ocean, and then all the material would end ejected towards the interior of the Arctic Ocean. And then what we see is that all this area can be very inaccessible for remediation during several periods of the year. So we think that this exposes the risks of this exploitation. So we have been also using this Lagrangian tool to identify in the Arctic Ocean this feature that is the transpolar drift that was object of study in a expedition, the Mosaic expedition, 2 years after this article was published. And then the transpolar drift is like a barrier that is highlighted by this very light feature that I am pointing here in the picture. And then is the responsible, this transpolar drift, of this very sharp salinity barrier that exists in the article that is separating saltier waters that come into the Arctic from Atlantic, and the Canadian Basin that here in this picture is at the left. So to explore truly the barrier effect of the transpolar drift in this slide, I have performed a simulation of 2 blobs at both sides of the transpolar drift. And what we see is that these 2 blobs really take a long time to mix. And after 2 years, they only mix here in this area, close to the land, to the North America coast. So as conclusions, I would say that Copernicus offers reliable ocean data and also satellite products that may be combined to offer sharp responses to important environmental ocean challenges. And dynamical system theories provide tools to do an interpretation of transport in these currents, and that in this presentation I have used these tools to identify risks in the Arctic coast of North America for oil and gas exploitation. And also these tools are able to identify the transporter drift as a barrier that maintains this salinity gradient between waters of the Canadian Basin and the Atlantic, as it prevents their mixing during long periods. Thank you very much for your attention.
Thank you very much, Anna, for your nice presentation. It was really interesting, and we have a few questions for you. So we will go to the Q&A session. It's more of open questions for now. Okay. So the first question is, what role could research on Arctic water dynamics play in preventing pollution from spreading to sensitive marine ecosystems?
Well, I have just tried to explain that, for instance, in this presentation, this is what we did to point out a risk, because to detect an area where whatever pollution happens in the coast is going to be spread in the interior of the Arctic waters, just because we have found this kind of object that I have been explaining, the hyperbolic trajectory, that corresponds to areas where there are strong contractions towards this hyperbolic trajectory and expanding towards the interior. So I think they can do a lot of role just to establish risks. And also, well, these tools, we have been using it not in the Arctic but in many other areas. For instance, at the beginning of September, in the Canary Islands, in a port, also we detected a leakage of oil from the port of La Luz in Canarias, and also the configuration was exactly the same as I have explained here, a detachment configuration where all the leakage of oil from one ship to another, when it was loading petrol, it was pushed towards the interior of the ocean, and then we were able to provide feedback to the emergency services, and to also to make it notice to many critical areas like fishing farms and things in the neighborhood. So I think it has a very important role.
Okay,
yeah.
Thanks a lot. We have this question about are Lagrangian models impacted by unpredictable Ekman spirals, Langmuir circulation, and others?
Well, the Lagrangian study I have done starts from currents from Copernicus that already have incorporated of all these effects to produce the currents. So my input are the currents from Copernicus that already have. So the Lagrangian models are affected because all these effects affect the currents, and then if the current change, the Lagrangian analysis also change. But my analysis is not adding anything else to the data that I take from Copernicus.
Okay, thanks a lot. The next question, if Lagrangian descriptors considered for path planning, how effective are they for guiding submarine navigation?
Yeah, this is a very interesting question. We have already done that in a transatlantic mission in North Atlantic. It is published in an article in in scientific reports in 2018 probably, or 20, yes, I think it was the same year as the article. And we were using exactly this tool for guiding the navigation of autonomous underwater vehicles in a mission through the North Atlantic, and they were very, very effective to accelerate the process, finding a concatenation of these hyperbolic trajectories that I have mentioned, and was speeding up the crossing a lot. You can read that. I can provide the reference. It's open access if you want.
Okay. Yeah, it's really interesting. So if you have the DOI, we can put it in the chat for the participant to take a look at. It's a really nice subject. Thanks a lot for the explanation. And this question: how could changes in temperature and salinity of transported waters affect Arctic algae communities, especially under climate change scenarios? So it's more of an open question again.
Yeah. I am able to study the physical part, but really I am not a biochemistry or marine biologist. So the impact on alga communities, I don't know, because there are a lot of biogeochemical processes involved on that. The only thing is that I can say is that we have used these tools also to predict the evolution of alga blooms, because I have not shown any, to predict the evolution, the material evolution of these alga blooms once they are formed. We did that last year also in the Canary Islands, because it was very interesting to know where those communities were going, because it was affecting fishing farms, because all these communities were taking out the oxygen from the water, and then it was a danger for them, and also tourism in the Canary Islands. So yeah, so thank you.
Okay, thanks a lot. Yeah, also the best way is to check a paper on biology also for this kind of question. Okay. And this question about so what is the resolution used for input geostrophic currents for the Arctics? 1/4 degree from CMM's global or better resolution? I don't know. Yeah, I don't remember which resolution you said you used.
I really don't remember the exact resolution, but it is on the paper for sure. Okay.
Yeah, we put the DOI on the InWeek chat for you to see, for the participants, and the papers are also uploaded on the home and program page if you want to take a look.
Yeah.
Okay, so yeah, check the InWeek chat and the home and program page. Okay, so that's it for the question for the presentation. Thanks a lot for the presentation and the Q&A session. It was nice having you. And
thank you very much for your
okay.
invitation.
Thanks. And okay, so Keguang, whenever you're ready, it's your turn to do the presentation. So you can, okay. And you can just turn on your mic and we can't hear you for now.
Thank you, Gaëlle, for the invitations. My name is Keguang Wang. I'm a research scientist in the Norwegian Meteorological Institute. Yeah, mainly doing ocean and CSIC modeling, data simulation, and predictions. It's my pleasure to introduce some of my research on this assimilation of CSIC concentration in high-resolution Pan-Arctic coupled ocean CSIC model, and share some of my experience in using the Copernicus marine data. Yeah, in this short talk, I will briefly talk about this background and the method, introduce some method, and show you some of the results using Copernicus marine data and other data to evaluate the model performance and compare the model results with other products basically, this paper is this talk is based on this published paper, which published on the Klaus Fair last year. So if someone will more interested, you can ask the questions later and also look into more details there. So it's quite, I think, well known. I think the Arctic is under global warming. Yeah, on the left side, we see this is the recent 30 years warming is much higher than the long-term atmosphere warming. And particularly we see the warming is around in the Arctic region. And consistent with this atmosphere warming is the rapid decrease in the Arctic sea ice thickness, as here shows mainly June to October, the summertime period, the sea ice extent in the Arctic 1980s to present. So it shows very clearly decrease of the Arctic sea ice extent. So this change actually is affecting strongly the Arctic climate and also ecosystems. And it's also opening new opportunities for the Arctic shipping and also Arctic natural resource explorations. So in order to better plan and manage the common activities in the Arctic, so we I think have a higher need to have high resolution models into different forms to predict the Arctic Ocean, sea ice, and other ecosystems. And here is one of our contribution towards this purpose. But mainly doing this sea ice data simulation. What we do here is we use this coupled high resolution pan-Arctic coupled hybrid coordinated ocean model. It's HICOM and the Los Alamos CS model, to do the simulations and possibly leading to the predictions. What is special here is we introduce quite a new data simulation method, which we call here as a local analytical optimal nudging. The main idea is to compare the traditionally quite widely used this optimal interpretation, three-dimensional variational method, and also it's very common now, I think, on some common filter. For like its observation, typically daily observations. In this new data simulation method, we apply this daily observation through all, like, for example, like the whole day. So it's mildly nudged into the model system. So given a very smooth evolution of the whole parameter evolution. And this is quite different from other data simulations, which only, I think, instantly estimate at the observation point. And this method is very efficient, 1% of the computational resources compared with on-summer common filter. So that's the main problem, I think, or a technical question remain here. How reliable or accurate of this method, or does it possible to be better in some future times, to be incorporated into Copernicus marine data some days. So for this purpose, we assimilated, apply this method to assimilate this advanced microwave scan radiometer, this called AMSA2 sea ice concentration, and gave some experiment to evaluate. So the evaluation basically I have put into two parts. The first part of this here is to evaluate how the assimilation of this ice concentration affects the model's performance, basically to see how it affects the sea ice concentration itself and sea ice thickness sea surface temperature and also sea surface salinity. Yeah, most of these data is from Copernicus Marine Service, excepted this ice concentration data. So what we have, like this is to show the effect of this assimilations of CS concentration on the CS concentration itself. So then we can see. So this is the observation, and this is the free run. So for the free run, if we compare the observations, it's in winter time it's quite close, but in summertime it's quite biased. And if we compare this line, there's assimilated results, and we compare this observations, it's almost no difference in terms of the monthly mean. Similarly, I think for the sea ice thickness, then this is cross theta 2 small ice thickness. It's weekly, and if we this data is not assimilated, of course, and from this is initial field from this free run, and this is assimilated one, and we see this initial field has some problems, I think, but after the data assimilation, I think after like 1 year, we see this is quite close to the observations, whether this no data assimilation still keeps a quite large bias in the field. And similarly for the sea surface temperature, this is a bias, so it's already removed, observed this Austria SST. Particularly in the summertime, there's these free runners very large bias in this Pan-Arctic coastal seas, and this assimilation really, I think, improved quite a lot of this. It's a very small bias now, I think. And similar, I think, for the sea surface salinity, this is a bit, I think, big problem still. I think, although it's this is the observations from the Copernicus data showing this institute analysis system sea surface salinity. So this is the uncertainties. So to showing how reliable of the data itself, but still, I think in the coastal Arctic regions still quite a large bias, but for when using the data assimilation, we can see like this in much of the Arctic region after 1 year. So it's this is the difference. So it's when combined together, it's closer to the observations. And the second part is try to compare with other CIS product. The main motivation was that because this typically like this passive microwave AMSA2 CS concentrations used for data assimilation, but this data is usually it's misses a lot of this low ice concentration area or thin ice area compared with the ice chart. So in this case, so we compare quite a different this CS concentration analysis from Siemens, this Copernicus data, and as well as some of these observations. And this is daily ice concentration. So this is the manual analysis data, and this is the model we assimilate, and this is a free run. And this is NEMO, it's a global model, Copernicus data, and this is older thing, Topaz 4, and this is NEXTIM, and AMSA2 and SSMIS, as these are both observations. So compare with this manually analyzed data, so we can see this even is it's really, I think, gives quite good results. And also we check the ice edge area, and also check the marginal ice zone area, and compare all the data. So really with this new data assimilation, we give the the lowest area for both ice edge and marginal ice zones. So, and also for some condition situations, if we need some like sub-daily like sea ice concentration or other parameters, this method can also be used. It gives a quite a smooth evolution and in the like early evolution or sub-daily evolution in case only like daily observations. So then conclude a bit. So this method is quite efficient method, and from this evaluation we really get this is quite effective in data simulation, and it's also improve other simulations of like ice thickness, sea surface temperature, salinities, and compare with other sea ice concentration product. And this new data simulation with the high resolution model, so provides more accurate sea ice edge and marginal ice zones. Yeah, thank you, Nati. Thank you for your attention.
Thank you very much for your presentation, Keguang. So we don't have any questions for now, so maybe
Okay.
everyone is looking at your
Yeah.
paper. We can wait a little bit to see if some of them are coming, but otherwise we will move on. So yeah, the link to your paper is on the in-week chat for the participant and was also uploaded on the website. Thanks you for sharing it with us. But yeah, I don't see any questions, so I guess we will move on to the next presentation.
Yeah.
Thanks again for your participation and
Yeah.
joining us. So Susanna, whenever you want. So the floor is yours for the presentation, and thanks again, Keguang.
Yeah, thank you.
Great, thank you, and thanks for having me. So I'm Susanna from the University of Vienna, and I will be talking mainly about energy and water fluxes in the Arctic Ocean and what challenges we face calculating them from ocean view analysis and what insights we can gain from ocean view analysis. So in general, oceanic transports, they are really important for the global climate by transporting water masses, nutrients, and heat around the globe. Also in the Arctic itself. So for example, for the Arctic, we have 4 major gateways where we have exchanges of water masses with latitudes further south. So we have warm, high salinity waters that flow into the Arctic Ocean via the Barents Sea opening and Fremd Strait. Then we have cold polar waters that exit the Arctic via Fremd Strait and Davis Strait. And we have low salinity waters from the Pacific that enter the Arctic Ocean via Bering Strait. And all those transports, they have some important implications on the Arctic system and changes in the Arctic system, including the ocean itself, including sea ice, and then in further consequences, also the atmosphere. So really an accurate monitoring of those transports is really important. And we have multiple mooring lines that really observe the deep water velocities and also other sea state variables like temperatures and salinities at those main Arctic gateways. However, those are quite limited in space and time. And this opens the need for accurate or credible transport estimates from other data sources, like, for example, ocean view analysis. So in our studies, we in general do use global ocean view analysis. So here from the Copernicus Marine Service, we have this nice ensemble of 4 ocean view analysis on a 1/4 degree grid, also called the GREP ensemble, consisting of 4 ocean view analysis from different institutes. And then additionally, we also have one higher resolution reanalysis with a 1/12 degree of horizontal resolution. Then apart from reanalysis, we also look a lot into climate models, but this is just a side note. So while we have those transport estimates from observations, gaining them from reanalysis is not always that easy for users, as ocean models generally use those quite weird-looking ocean modeling grids, as seen here, for example, to the right. in order to avoid singularities over the ocean. So here, for example, we see a tripolar grid where instead of one North Pole over the ocean, we have two North Poles over Eurasia and North America. And then we get those weird looking band grid lines in between. And those like band grid lines, they present some difficulties and challenges when calculating transports concerning the directions of the flows. So, I mean, we can see that if we move towards the direction of one of the artificial North Poles, we actually do not move towards the true north anymore. So this poses some challenges concerning the signs of the velocity components. But we also have some other challenges with those grids. And there are many different grid types in use. So for the Copernicus Marine Service, for the global reanalysis, they all use a tripolar grid, like similar to this one. However, there are also like dipolar grids where the pole is shifted southwards, mainly over Greenland, or there are also, for example, triangular, so unstructured grids, where we also avoid the North Pole. Now, the simplest way, of course, would be to interpolate those grids onto regular grids. However, that is not possible for the velocity components that we need for the transports, as we would get quite large interpolation errors, as those interpolations of the vector components would hurt the conservation properties of the models. So here to the right, we can see those are just volume transports via a section in the North Atlantic called the rapid section. We can see transports calculated on the native grids at the black and the red line, and we can see transports calculated when prior to the transport calculation, we regrid or interpolate the data onto a regular grid. So we can see we get quite large errors doing this. So we can't do this. We really have to calculate the transports on the native grids. And talking to different users, we found that this could be really challenging and time-consuming when dealing with a large ensemble of data and a large amount of different straits. And therefore, we've invested some time and created straight flux. Those are quite easy to handle Python tools for the exact calculation of volume, heat, salinity, and ice transports in the oceans. They work for different reanalysis, for example, or reanalysis in the from the Copernicus Marine Service, and also for climate models, for example, from the Climate Model Intercomparison Project Phase 6. I won't go into the details behind the calculations. However, just to mention, we have two main functions. The first one really provides the net integrated transports through desired sections just by supplying the coordinates of the sections. For example, if we look at Frem Strait between Greenland and Svalbard, we can really assess, here we see the volume transport, so we can really assess the volume that is being transported via this section. We, for different reanalysis, all of the colorful lines, and derived from available observations, the blue line, the black line, sorry. So we see that in general for these sections, the reanalysis are actually biased low. And to further assess this, we can use the second function of straight flux, which provides us quite nice cross sections of the vertical plane. So here we see the currents that flow in and out of the Arctic via Frem Strait. So to the right, we can see the eastern part of Frem Strait. To the left, we can see the western part of Frem Strait. So we can see the inflowing currents in the east and the outflowing currents in the west. And now using straight, so this is from observations. Using straight flux, we can directly compare this to the output from the ocean reanalysis. So here we see the difference between observations and the higher resolution GLORIS 12 product. So we can quite nicely assess where are the currents too strong, where are they too slow. Yeah, we have used straight flux for multiple different case studies around the globe. Here, of course, I will focus on the Arctic ones. So first of all, back in 2022, we've assessed quite thoroughly the Arctic water budget, mainly from, let's call them observation-based data sources. So to the left, we have a schematic of the water budget focusing on the ocean. We've already heard this. We have an input of fresh water from the atmosphere to the ocean via precipitation minus evapotranspiration. Then, of course, we have an input of water from the Arctic lands via runoff, and we have exchanges with latitudes further south via those oceanic transports They can be in liquid form or also as sea ice. Now, in this study, we combined all possible observation-based data sets. So we used in situ observations, satellite observations, reanalysis, and for those oceanic transports, we used ocean reanalysis to really create updated estimates of all the budget components. And using a variational optimization scheme, we really get closed budgets, so with residuals of 0, with best estimates of all budget terms, including uncertainty estimates for a longer time period. So I think this was for 1993 to 2019. And this wouldn't be possible without those ocean reanalysis, as the observational data sets that really only cover a shorter period of time for the transports. Now, using this as a baseline in another study, so in a study from last year, where we assessed the Arctic energy and water budgets from reanalysis and climate models. So here we see to the left, the heat transports really integrated over all 4 Arctic straits. So this is the net heat that flows into the Arctic Ocean from latitudes further south. The seasonal cycles to the left, and to the right, we can see long-term averages. The black bars are always the long-term averages. So heat transports in the bottom and volume transports in the top for different models. Then the last black bar shows the mean of the GREP reanalysis, and the blue bar shows the observations. And here to the left, we also see the black line shows the mean of the GREP reanalysis, the black dash dotted line from observations, however, over a shorter time period. And the colorful lines show the models from CMIP6. So what we see in general, the reanalysis, they perform reasonably well. We have a low bias in the later part of the year. However, in general, the performance in long-term averages and also in the variability, which is not shown here, is quite good. But on the other hand, the climate models, they are all over the place. So we have really large uncertainties. We have really strong biases for some models. And those biases, they are not only constrained to the transports, but they, in the next step, also prevail to other quantities, like, for example, sea ice or also the ocean warming rate. So it's really important to get those transports correct in the models and reanalysis. And then just a glimpse of another study that we did last year. So this is part of the Copernicus Ocean State Report 7. So here we've assessed the transports through the Greenland-Scotland ridge. So this is a little bit further south between Greenland, Iceland, and then moving over to Scotland. It's still a very important section when it comes to the heat inflow from the Atlantic into the Nordic seas and then moving further north to the Arctic. Again, comparing observations, the red line, to different reanalysis. So here we see the heat flux anomalies via the whole section. We find generally quite a good agreement, not only for the whole section, but especially for the single branches of the Greenland-Scotland ridge, in terms of variabilities of long-term averages and also seasonalities of volume and heat fluxes. However, for the net heat flux, we actually find quite a strong low bias in the reanalysis, as seen here to the right in the table. So we see that virtually all reanalysis, they clearly underestimate the values that are provided by observations. Now we can make use of the second function of straight flux, so we can really assess those nice cross sections of the vertical plane, and we can divide the water masses concerning their properties, so concerning the temperatures, salinities, and densities, into Atlantic waters, so warm, high salinity waters coming from the south, into overflow waters and into polar waters. And we found that this low bias in the reanalysis is actually caused by an underestimation of the Atlantic water inflow into the Nordic seas. And yeah, in many of our case studies, for example, also in this one, we found an indication that the higher resolution reanalysis, so GLORIS 12, actually shows a little bit of a better performance here in this study, especially for the Atlantic water inflow. Yeah, in other studies, we also found that this is quite strongly connected to the bathymetry of the straits. So the narrower and the more the more complicated they are in their bathymetry, the better the better the performance of the higher resolution reanalysis is compared to the lower resolution reanalysis. So already summing up, so we've developed those straight flux tools, which really allow for a fast and consistent comparison of transports to observations, consistent with the discretization schemes of the models. This allows us for a lot of validation and analysis works. So we can assess the transports, we can assess the ocean's vertical structures, we can also assess the meridional overturning circulation. And we've performed many case studies in this direction where we already showed the usefulness of the reanalysis when analyzing transports. However, there are also still some biases and uncertainties that prevail. And this opens the need for larger intercomparison projects as they were done already and are planned. For example, there's a big intercomparison project planned for next year. To assess those ocean reanalysis, where do they perform good, where do they perform bad, and how can we improve them? Okay, yeah, that's all from my side, and I'm happy to answer any questions.
Thanks a lot for your presentation, Susanna. It was a really nice presentation. So we have a few questions for you. So we will move to the Q&A. The first one is, what was the type of chart in which Susanna represented the currents? So if I'm not mistaken, it was on the slide with the Hofmüller graphics on the straight flux slide.
You mean this vertical structure of the currents? Yeah. So this was just like on the y-axis, you saw the depth, and on the x-axis, you saw the distance along the strait. So for example, if we look at Fremd Strait between Greenland and Svalbard, we really see the profile, the depth profile of the strait, and we can assess the currents that flow in and flow out in all depth layers in the strait.
Yeah, it's a really nice way to do vertical visualization. So this one, both of the questions are coming together actually. Is the Python package for straight flow already in Copernicus, and are data from Copernicus already corrected by that package, or do we have to install it and do it ourselves after downloading the data from Copernicus?
So you have to do it yourself. So the package is quite easy to handle. You can just download it using PyPy, for example, Python. And if you use the native grid files, which I would highly advise if you are dealing with transport calculations, then you have to use the package yourself using the data that you downloaded. But it's really easy to handle. You just input your data. You just input your coordinates that you need for the strait. So, for example, for Fremd Strait, the coordinates from the eastern point, from the western point, and from the eastern point, and then the package does all of the calculations. So it's really easy to handle, but it has to be done by the user. Yes.
Yeah. Okay. Thanks a lot for the explanation. So, yeah, both of them were the same question. We don't have any more questions for now. We can wait a little bit to see if some of them are popping, but thanks again for your presentation. We put all of the links and DY you provided on the chat and on the website, so thank you very much.
Thank you.
I think we can close the meeting. So thanks again, Susanna, for your participation, and to Keguang, Jiping, Anna, and Rezak. So yeah, for the unanswered questions, so the technical question for the Copernicus Marine Service and all of the other, we do a post-event report with the unanswered question where we put links and articles and everything you need. So it will be available in 1 week, 10 days with all of the replays and PDF presentation. So yeah, we are arriving at the end of the session. I hope it was an insightful session. So as you know, the practical session will be tomorrow. So if you haven't had time yet, I invite you to check the full tutorials to get ready for it. So they are available in full on the event website. There is a tab at the top where you can find Jupyter, QGIS, and Air section. So yes, like here. So all of them are using the Copernicus Marine data. There you can download the tutorials, and there are also videos of the full demonstration, so you can follow and practice, because tomorrow it will be only a summary of the tutorials. So if you want to check the full tutorials and have questions, you can go check. Also, before you leave, I just want to remind you that there is a section on the website next to the Q&A, which is reserved to the polls. So we would really appreciate to have your feedback on today and what you could provide in the future. So if you could take 2 minutes of your time, that would be really helpful. And yeah, so we will put the replay of today on the website, and that's it. So thank you to everyone again, and see you tomorrow, and have a nice day. Goodbye.